So in the previous modules, we've been discussing an interesting quantum experiment, and we were building our way up to how do we actually mathematically represent quantum states so that we are able to explain the outcomes of the experiment. It turned out that we were sort of finding a way into describing quantum states as probability vectors. The coefficients of those vectors, when squared, would perhaps represent the probability of expecting particular outcomes. But we're going to now gradually make these ideas a little bit more precise. Let's quickly recall one such experiment with the apparatus oriented along the z direction, which we refer to as the z apparatus. Now it turns out that if I have a quantum state as the input to the z apparatus, and let's say that quantum state is already pointing in the positive z direction, and I pass it through the z apparatus, nothing really happens. What comes in goes out completely undisturbed. Likewise, if I have an arrow, which, by the way, these arrows are just simplistic physical representation of what might be quantum states, but we don't have to take them very literally. And again, I'm going to talk a little bit more about why that is the case. But let's say I have this down pointing arrow, which is pointing along the negative z direction, and I again pass it through the z apparatus. It turns out that this arrow also comes out completely undisturbed. However, as we've seen in the previous modules, if I have an arrow pointing in the positive x or the negative x direction and I pass them through the z apparatus, I have complete lack of knowledge on what to expect at the output of this apparatus. There is a 50% chance that we'll see an arrow pointing up along the positive z direction and a 50% chance that we'll see an arrow pointing down along the z direction. However, point to be noted is that the output of the z apparatus will always give me an up arrow or a down arrow. The only variable which we are trying to figure out is with what probability do I see an up arrow and with what probability would I see a down arrow. Now let's say I have an arrow which is representing a quantum state prepared in a way that it's making an angle theta with the z direction. Now what does it mean to prepare a quantum state? Again, we're going to come back to this in a future video. For now, think of this just as an arrow in space which is making an angle theta with the z direction. Not quite accurate, but let's go ahead with it. So I'm going to send this arrow through the z apparatus. Now again, at the output, I'm still going to see something either pointing up along the z direction or something pointing down along the z direction. However, if I repeat this experiment with many such arrows, all of them initially making an angle theta with the z direction, and I calculate the probability to observe an up arrow, it turns out that that probability is cosine square theta. Now recall that if I think of these arrows as a vector in space, then the projection of this vector along the z direction is cosine theta. And this is what we were talking about in the previous module, that somehow if I think of these quantum states as vectors, perhaps their projections along the basis axis when squared gives me the probability to observe an arrow which is pointing, let's say in this case, pointing along the positive z direction. However, if I do this experiment, it turns out that while cosine square theta rightly tells me the probability of observing an up arrow, sine square theta tells me the probability of observing a down arrow. Now, if this was really a vector in the way that we have represented here, then cosine theta is the projection of this vector along the z direction, whereas sine theta is the projection of this vector along the x direction. So it's not true that sine square theta is the probability of observing a right arrow in this case. And this is a point that I hope you will think a little bit more about. So cosine square theta will be the probability of observing an up arrow, and sine square theta is the probability of observing a down arrow. And the only outputs I can see out of the z apparatus are either an up arrow or a down arrow. And that brings us to a very interesting question. What is the right mathematical object for us to represent this quantum state? Even if we want to represent this as a vector, what is the right basis to represent this quantum state as a vector? even more interestingly, how do I represent the physical device that I am depicting in this particular experiment? For instance, the Z apparatus seems to be doing something to these quantum states. So what is the mathematical object with which I can represent such physical devices? So let's see how we can do that. So the question for us is, what is the right mathematical object with which we can represent the quantum states and the physical apparatus with which we've been doing these transformations or bringing about these changes to the quantum states, so that we are best able to capture the observations from the kind of quantum experiment that we've been doing. It turns out that if I represent quantum states as vectors, and to be a little bit more precise, we can call them probability vectors, then the physical devices which are performing some changes or transformation onto these vectors can be represented as matrices. It turns out that this is true, but the interesting thing is, what is the right way of expressing those vectors, and how do I represent, let's say, the matrix for the Z apparatus so that I'm able to describe the observations from the quantum experiment that we've been doing. So that's the discussion for the next part of the module.